Hello, everyone. Welcome to pre-lecture 11. This is going to be the start of chapter 13 for us, looking at our introduction to equilibrium. And so thus far, with most of the chemistry we've discussed, we've been talking about reactions that are designated with a reaction arrow shown right here, where we have our reactants on the left side, our products on the right side. And generally speaking, these are considered irreversible reactions, meaning that they pretty much only go one way. However, there are some chemical reactions that are actually quite reversible. And this means that they can go both ways, and assuming they are left to their own devices, they will end up in an equilibrium state. And we would designate this in a chemical equation with this double-sided arrow, where we have one end going towards our products, and then we have another arrow stating that the reverse reaction is also feasible, where we would have our 2NO2 going back to our reactant of N2O4. Okay? And so the relative concentrations of these reactants and products will vary greatly. Sometimes your reactants are favored, sometimes your products are favored. But for most systems, you will get a good mix of both your products and your reactants when equilibrium is achieved. Okay? And so if we contrast this with what we just learned in chapter 12, kinetics was all about how fast a reaction goes. And what equilibrium tells us is how much of the products and reactants we will end up with. And once we have determined that, we have figured out the states in a dynamic equilibrium. Okay? And so that is essentially the way that kinetics and equilibrium are connected, is through this idea of dynamic equilibrium. And so when a dynamic equilibrium has been reached, it doesn't mean that we no longer have any chemistry going on, just means that the rate, so again, rates are kinetics, but the rate of the forward reaction and the rate of the backward reaction are equal. And so you could see here, we have basically our concentration versus time. And so these are determined to be our equilibrium concentrations. You'll see that we have some amount of each of our products. And then again, once equilibrium has achieved, that just means the rate. So we would designate that with our lowercase f right here for our forward reaction, lowercase r, kr for our reverse reaction. Those rates are also equal. Okay. And once this dynamic equilibrium has been reached, the quantity of our products and reactants will not change unless there is some sort of outside disturbance. And so that can be a change in temperature, change in pressure, or if we add more chemicals, that can also shift the equilibrium. Okay. And so in addition to chemical reactants, where we're going between our reactants and our products, equilibria also exists between phases of matter. And so if you think back to chapter 10, I guess, and how vapor pressure was defined, that is a term where when we have reached a dynamic equilibrium of a gas going in between a gas and a liquid, vaporizing and condensing at the same rate. And so those are said to be in dynamic equilibrium. And so shown here on the right is this ampule containing the chemical bromine, Br2, and it is in an equilibrium between its liquid and its gaseous states. And so we could also define that with our equilibrium arrows. Of course, we don't have a chemical reaction here. We just have a physical change going between liquid and gas and liquid. Okay. All right, and so this being Gen Chem 2, of course, we want to quantify this relationship. And so one of the ways that we would define the status of a reversible reaction is through the reaction quotient, which we designate with an uppercase Q. And ultimately, this is derived from the stoichiometry of any reversible reaction. So if we have A plus B, yields C and D, as well as C and D can perform the reverse reaction to reform A and B. And then the lowercase letters representing their stoichiometric coefficients, we would define our reaction quotient as products over reactants raised to the stoichiometric coefficients. And so again, those lowercase letters are just our stoichiometry in front of our products or reactants. And so one of the mantras that I'm going to say a lot for this chapter and all of next unit is products over reactants. And so that is how we define Q, as well as another term that we'll get to in a moment here called K. And so if any of our products or our reactants are gaseous, we can also, in addition to expressing Q in concentration, so again, our brackets would indicate concentration, we can also express our ratios between our reactants and products in pressure, in particular partial pressures. And so again, this would just be the partial pressure of C raised to the stoichiometric coefficient of C. Okay, and we'll get to some more solid chemical examples here in a moment. And a side note on units is that any reaction quotient will be unitless. So say you had, ATM times ATM over ATM times ATM squared. You wouldn't say that your final units are just going to be 1 over ATM. Anything you see here that's our reaction quotient is not going to have any units. So it's going to be a unitless quantity. The reason for that is beyond the scope of this course, but if you just trust me and know that you don't need units for this reaction quotient, that is something you need to know. Okay. And so what the numerical value for Q ultimately describes for us here is the quantities of our products and our reactants and the ratio between them before our equilibrium has been reached. And so this is key, that Q, our reaction quotient, is representative of non-equilibrium conditions, okay? And so, for example, we have this line here that tells us when an equilibrium is reached in time. And so any time before we hit this dotted line is represented by our reaction quotient Q. Okay, and so say we started a reaction with no product being formed, and since we always, or no product being present, sorry, and since we always have our product over our reactant for our quotient here, 0 divided by anything is going to be equal to about 0, right? Whereas if our reaction goes to near completion and say we have basically none of our reactant left at the end of a reaction, then if you divide anything by 0 or anything close to 0, it will equal about infinity, okay? And so again, Q is just representative of any of our product and reactant quantities expressed as a fraction prior to equilibrium being reached. And so once a system does reach dynamic equilibrium, the reaction quotient will then be equal to Q, or will be equal to K, sorry. And uppercase K is our equilibrium constant. And so this can be a confusing unit sometimes just because we have uppercase K when it comes to equilibrium, whereas we've just been talking about lowercase k to represent a rate constant for kinetics. And so that's just something that it's the way they're defined, and it's something you'll have to keep straight. But anytime you see uppercase K, that is indicative of our equilibrium constant, which again is same thing as Q, just our products over reactants raised to their stoichiometric coefficients. It is just once we have reached equilibrium, we express it as K, right? And so since K is expressed as a fraction of products over reactants again, larger K values will indicate that more products are formed. And so as long as our K value is over 1, because of course when we'd have more products than reactants, then we would say that our K value is more than 1, our product side of a reaction is favored. Whereas if K is less than 1, that means that our reactant side is favored. And so we would have more of our reactant present than our product. Okay. All right. And so there's a little bit more to talk about here before we call it a video, and what I want to talk about now is how we would consider homogeneous equilibria. And so these are equilibria where all of our reactants, products, catalysts, anything else are in the same phase. Okay, and so for expressions like this, say we had the C2H2 plus 2Br2 yielding C2H2Br4, all in aqueous solution, then we would just write our equilibrium expression that our equilibrium constant K, the sub C is just to indicate this is a concentration-based measurement as opposed to a pressure-based measurement, which we'll get to in a moment. And then we just put our products over the reactants raised to their stoichiometric coefficients. And so we would add the Br2 squared there because we have a stoichiometric coefficient of 2 for our bromine. Okay. If we have K sub P, that would indicate that all of our reactants and products are in the gaseous phase, and so we're measuring their pressures. And so we could express that as a concentration if we're able to measure the concentration of our gases, or we could express it again in their partial pressures. And so it will depend on what sort of units you would be given there. Typically, if everything is gaseous, you would want to have the units, pardon me, you would want to measure everything in partial pressures. Okay, all right. And so sometimes we occasionally will need to convert between Kc and Kp. And again, that's just concentration or equilibrium constant for concentration and equilibrium constant for pressure. And so we can do that by setting Kp equal to Kc times RT, our gas constant, and the change in moles, which is delta N here. And so that is equal to the difference in molar amounts of product and reactant gases. So for example, if we were looking at this equilibrium here, we would say that we have 4 moles of gas on this side, we have 2 moles of gas on this side, and so delta N would be 2. Okay. All right. So finally, want to talk about heterogeneous equilibria. And so this is when our reactants and products are not all present in the same phases. Something else to take note of here is that any pure liquids, which of course we would designate with the phase symbol L, or solids, are not counted as part of equilibrium expressions. And so the reason for that is, again, a little bit beyond the scope of this class, but if you take my word for it, just remember that any pure liquids or solids are not a part of our equilibrium consideration. And so if you have something like a solubility product here where we have lead chloride that can dissociate reversibly into lead 2 plus and chloride minus, then our equilibrium expression would just be our products because our reactant is a solid and so it is not soluble. And because it is a solid, we would not count it in the equilibrium expression. Okay. The reverse of that, so if our product is just a solid, then and we only have one gas, then we would just put 1 over the concentration of CO2. And finally, of course, we would have some other examples here. And so we have this phase change we saw earlier where, again, we're just going between a liquid and a gas. And the only thing that will determine that equilibrium constant is the concentration of bromine that is present, which again, we could also define as the partial pressure of bromine. Okay. All right, that's it for this video. Again, if you have any questions, please feel free to email me or write them down and we can discuss them in class. Hope everyone has a good day and I will see you soon.